We are talking about section 3.6 today, graphing rational functions. So quick review, just a general definition of rational functions. They are fractions with x's in the denominator. So for example, you might see something like this. This is an example of a rational function. You've got a fraction and you've got an x in the denominator. These behave differently than polynomials, and so we've got a different set of a game plan for graphing these. So I'm going to list that out and then we'll go through each section. So the first thing that you're going to do is very much like polynomials. You're going to graph your x-intercepts and your y-intercepts. And I'm going to make this list and kind of do it as I go. So x-intercepts, the plan is not changed. You need to plug in 0 for y. So we plug in 0 here. And you can clear your fractions by multiplying through by your denominator. These cancel. I get 0 on the left. And when I solve this, I'm going to add 3 to both sides. So I'm going to get x equals 3. That's going to be my x-intercept. First step. Second step, I'm going to find my y-intercept. So I'm plugging in 0 for x. That's going to give me -3/2. That's my second step. My third step is to find what is called my vertical asymptotes. And the way that you find your vertical asymptotes are they're the places where your function is not defined in the domain. And if you remember when we talked about domain with fractions, the issue is where the denominator equals 0. So the way you find the places where your function's not defined is you set your denominator equal to 0. So I'm going to write that here. This is the game plan. Set the denominator equal to 0. That's how you find your vertical asymptotes. So you want to throw that on a note card on the front. You want to put find vertical asymptotes. On the back, you want to put set the denominator equal to 0. You have to memorize that connection and that instruction for what to do. So I'm going to do that here. Take my denominator out, set it equal to 0. So x equals -2. This is my vertical asymptote. Now, this is asymptotes are equations of lines. So this right here is an x-intercept. This is a point on the axis. But a vertical asymptote, this is x equals -2, the line. This is a line, right? We'll draw this in a minute. Let's go through the whole list though. The fourth plan is to calculate, well, I'm just going to say find the horizontal asymptotes. This is a little bit more complicated, and I want to take some time to talk about what's happening here. Horizontal asymptotes are lines that dictate where this function goes for very large numbers of x and very small numbers for x. So, for example, if I was to draw a graph here, it's what happens way out here and what happens way out here. Now, it is an asymptote, so it is a line at the end of the day, but the line is kind of like a boundary marker for the big and small numbers of x. So what we do is we take something called a limit. The concept of a limit is what's happening as x gets close to a certain number. So for example, if I take the limit as x goes to infinity, this is the notation, it's LIM, and under we go x goes to infinity. What that means in English is what is happening when x is big. Now, the problem is infinity is not an actual number, so we can't plug infinity in. It's a concept. It's like as it goes forever. And so we have to talk about a limit because we don't actually ever get to infinity. We just approach infinity. And that's the idea of a limit. It deals with places in a graph where we can't actually be, but we could be close to. So the idea is what happens when this function, and the limit always has a function that it's attached to like this. What happens when x goes to, say, 1,000,000, okay? And the problem is that when you're adding and subtracting numbers and they're in a fraction form, it's hard to tell what happens as x goes to 1,000,000. So we do a little trick, and we always do the same trick for this, and you will also do this in calculus. We take the function and we divide everything, every term, by the highest power of x in the denominator. So I'm going to write that down. What we're going to do for the horizontal asymptote, I'm going to write it under here. Let me erase this. We take the limit as x goes to infinity. That's the first thing that we do of the function. And then we are going to divide every term by the highest power of x. All right, so in the denominator. So downstairs I'm looking at, okay, highest power of x is x to the 1. So what I'm going to do is I'm going to keep the limit on here because that's what we're going to look at. What happens when x gets big? I'm going to divide every term by x. And this is a trick that you will use again in calculus when you're taking limits as x goes to infinity. You'll see this again. So this benefits you to kind of understand this concept. It'll make it easier next semester. Now, reduce. So let's put that in the list. Next thing we do is reduce. And let me show you what happens when, this is kind of a trick, and what happens when we do this. Now let's talk about what happens when x gets really big. I want you to pull out your calculator, and I want you to calculate 3 over a really big number. You know, just plug in a bunch of zeros, okay? So let's do that really quick. 3 divided by really big number. What happens? Look at our answer. 3 times 10 to the negative 17. That means move the decimal 17 places to the left. Essentially, what is this value? This is, if we round it, we would round it to 0. It's 0.000000003. Okay, so it's essentially 0. So what happens as x in the denominator gets really large is that this fraction becomes 0. Now look, if it's not very large, whoops, hold on. Let's kind of take a few zeros off of here. I mean, 3 divided by 10 is 0.3. That's not 0. That's definitely farther away from 0. But as I add another 0, it gets smaller and smaller and smaller. See how that's working? And as x gets bigger and bigger and bigger, then I start getting closer and closer to 0. That's the idea. So what happens as I take the limit of this function here? Well, 1 doesn't change. 1 is just 1. But when I plug in a big number for x, now I can't plug in infinity, but if I plug in as x gets bigger and bigger and bigger, this little part of the fraction becomes really not important because it becomes so close to 0 that it doesn't really even register on the scale. All right. And similarly, in the denominator, the 1 doesn't change, but as 2 over 1,000,000 is very, very close to 0, and so this becomes also negligible. So what I'm left with is this, which equals 1. And this is our horizontal asymptote. That's how you find a horizontal asymptote. You say, what happens? You do the little algebra trick so you can get it in fraction form, and then you say, what happens when I have really big x's? Now, we'll do a bunch more of these, so if that's, I understand that's kind of a weird concept. It's the first time you've seen that probably, so be patient with yourself. We'll do a couple more, but at this point, this is our step 4. This right here is the horizontal asymptote. Call it HA. And it's an equation, it's a line, and it's a y equals line. And this is the y equals line that the graph is getting really close to as x gets really big. Okay, and the 5th step in our list is plug in extra points, and this is as needed. So not all problems need you to do this. Okay, now let's draw and say, okay, what the heck's going on? What does all this mean? Let's draw a picture. So now we're going to go graph the function. So first of all, my x-intercept is at 3, and my y-intercept is -1.5. So here and -1.5. So it's going to go through those 2 points. My vertical asymptote is a line at x equals -2. Now what this line is, vertical line asymptotes are lines that the graph cannot touch. Okay. And then the horizontal asymptote right here is a line of y equals 1. And what this line is doing is it's guiding the graph way out here and way back here. So as I extend out, the graph will be, it kind of acts like a magnet. It magnets the graph to it. Okay. Now, what's the general shape of these functions? Well, you know one of them. We memorized 1 and 3, 1. What's this look like? That was one of your parent graphs. That's a rational function, by the way. It's got a horizontal asymptote at 0. It's got a vertical asymptote at 0. And it looks like this. So this is kind of the general shape of these graphs. They're swooshy things, as I like to call it. And what you're trying to do in your picture here is figure out what quadrant your swooshy things are in. Okay, so this vertical asymptote, let me do this in a different color. Vertical asymptote divides the graph into left and right. Okay, see that? There's a left side of that and right side. And the horizontal splits it into top and bottom. So, oh my gosh, spelling. Sorry, hold on. So what these dotted lines have done is they've divided us into 4 quadrants. Now, it kind of ignore the x and y axis. Here's the quadrants. Here, 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 and here. And your question is, what sections are the swooshy things in? All right, good question. How do we know? Well, if there's points in one of the quadrants, you know you're drawn in that quadrant. So I see here I've got x and y intercepts. So I'm going to draw a swoosh in here. And it goes through those points and it generally kind of starts magneting to the asymptotes as you go out. Okay. Now, would the graph be in this section up here? Hopefully you're thinking through it and saying no. Why? Because if I drew a swoosh in here, 2 things would have happened. 1, I would create another y-intercept, which is not true. I mean, this told me that my only y-intercept was -3/2. That means the only place I can draw cross the y-axis is right here. That's the first problem with drawing a swoosh up there. The second problem is this thing does not pass the vertical line test. It's not a function. So you will never have 2 swooshes, one on top and one on the bottom of each other. They'll always be next door to each other. Okay, so that means that we can back up and say no swoosh up top. Now let's go over to the left side. Where do I draw? Do I draw in this top section or this bottom section? We just figured out that we can't do both, right? Because if I draw in both of these, it won't be a function, so it's one or the other. If I draw here, look what happens. What did I create? I created an x-intercept, and my math told me that this is the only x-intercept. So that means that my swoosh can't be in that quadrant. So that means it must be up here. And I don't care how close it is, you know, what the slope is of that, as long as it's kind of a swoosh and it's growing towards the asymptotes, that's fine. And this is the graph of the function that we started with. So you can see it looks similar to our parent graph, but it's been shifted and flipped around a little bit. Okay. All right, let's try another one. Oh, let me say one other thing before I go on. This extra note, step 5, plug in extra points as needed. That's just if you kind of have trouble deducing which section it's in, you can always plug in XY coordinates. It does make it take a little longer, so be aware of that. But if you wanted to, like say you weren't sure if we were going to be up here in the upper left or down here in the lower left, you could plug in a point, like let's say 1, 2, 3, 4, -4. If I plug -4 into the original function, I would get a -7 over a -2, which is a positive 3.5. So I would go over here and go 1, 2, 3, 4, positive 1, 2, 3.5, and there we go is a point that is on the graph that I drew. Okay, so that's kind of a way to check yourself, make sure that you pick the right section, or if you're unsure for some reason. All right, let's try another one. Okay, let's go through our list. This list, by the way, you need to memorize. You need to, when I say graph and you see that it's a rational function, you need to come up with a list in your head. First thing, X-intercepts. So I'm going through the steps in my head. X-intercepts, I'm going to set this equal to 0. Multiply through by the denominator. These cancel, and this is going to be 0. So x is going to be 2. That's going to be my x-intercept. Second thing on my list that I have memorized is my y-intercept. That means plug in 0 for x. All right, that gives me a -2 over -12, which is a positive 1/6. That's my y-intercept. The third step is to find my vertical asymptotes. And the way I do that is I set my denominator equal to 0. Now you can see where if you don't have that memorized, you're going to struggle with what do I do next. So you have to have that memorized. When you say vertical asymptotes, in my brain I say that's where the denominator equals 0. I have that memorized. If it's a polynomial, you're going to need to factor it. All right. Hold on a sec. My pencil stopped working for a second. Okay, there we go. So that means that x is going to be 4 and -3. So in this case, I've got 2 vertical asymptotes, which is possible. Now let's go through this horizontal asymptote procedure again and just check ourselves. So I'm going to take the limit as x goes to infinity of this function. X minus 2 over x squared minus x minus 12. Okay, now we next divide this function by the highest power, every term by the highest power of x in the denominator. So I'm going to divide everything by x squared. Now, why can I do that? Because I'm dividing the top and the bottom completely all by the same thing. So basically that means I'm just multiplying by 1. So I'm not changing the value of it because I'm doing it to the top and the bottom in every term. Then reduce. X over x squared is 1 over x. This stays. X squared over x squared is 1 over x, and this stays. Now, let's talk about what happens when x gets really, really big. Basically, anything in fraction form here goes to 0. 1 over a million, that's roughly 0. Okay? 2 over a million squared, that's even more 0. The 1 is going to stay. So I've got 0 on the top, I've got 1 on the bottom. This guy goes to 0, and this one also goes to 0. Because even though there's a 12 on the top, 12 doesn't even compare to a million squared. It's still going to be really, really small as x gets big. So this reduces then to 0. My horizontal asymptote is going to be y equals 0. Now let's draw all of these situations on a graph. We've got an x-intercept of 2 and a y-intercept of 1/6. So right about like that. I've got a vertical asymptote at 4 and -3. And I've got a horizontal asymptote at 0. Now, some of you guys might be concerned. You might have noticed this situation. I've got a horizontal asymptote and I've got an x-intercept on that, which means that it's going to touch the asymptote. That's fine. Why? Because the horizontal asymptote only binds the graph way out there and way out there. It does not bind the graph in here. Remember when we did that on the calculator, we plugged in 3 over 10, and that's 0.3. That's fine. It's doing normal things in the middle. It's when I plug 3 over a million that I get roughly 0. So we are only saying that this asymptote is going to bind the graph at the extremes, but not in the middle. Now, the vertical asymptotes are different. They are actually undefined. So this graph will never touch the vertical asymptotes. So it can go through a horizontal in the middle, but not ever the verticals. All right, now let's talk about how to draw this. These are a little bit different than the previous ones we did because if you'll notice, we've got now 6 sections. I've got 1, 2, 3, 4, 5, 6 sections here, okay? The outside 4, 1, 2, 3, 4, act like these 4, okay? So you're going to have swooshes in one of those, top or bottom, and then this middle section is going to do something different. We'll talk about in a minute, okay? So let's deal with these outside 4 first and figure out where we're swooshing. This type of problem is where the last step 5 comes in, where we say plug in extra points as needed. Look at this. I can't tell where the swoosh is supposed to go. Is it here or is it here? I don't know because I don't have any x-intercepts and neither of these create x-intercepts. So I can't use that reasoning that I did on the last problem. In this situation, I do actually have to plug in an x coordinate and calculate it. So what do I want to choose? I want to choose an x value that's in this section. So 1, 2, 3, 4, 5. Let's say plug in 6. That's an x value that is out far enough to be in these outer 2. And I'm going to plug that into the original function. So I've got 6 minus 2 over 6 squared minus 6 minus 12. So that's going to be 4 over 36 minus 18. So I don't know, that's a positive number, yeah? 36 minus 18, you can calculate if that you want, but all I care really about is at 6, am I positive or am I negative, right? So all you care about is the sign. You don't really, I don't really care what the number is. So if at 6, I'm up here somewhere, that means that I'm going to pick the top swoosh. and the bottom one is not part of the graph. Okay? Again, if you want to calculate the exact number, that's fine with me, but these graphs are not intended. What I'm grading on these graphs is, are all your parts labeled correctly, X, Y intercept, asymptotes, and did you put your swoosh in the right section? That's what I'm looking at, okay? Now let's figure out what's happening over on the left-hand side. I also am going to need to plug in a point here. So I'm going to pick an X value that's 1, 2, 3, 4, like let's say -5 here. Make sure it's out in that left-hand section. So if I plug in -5, I'm going to get -5 minus 2 over -5 squared minus a -5 minus 12. Okay? And that's going to be a -7 over 25 plus 5 minus 12. This is definitely a positive number, and this is a negative number, so this is going to be a negative value. Okay, again, I don't care if you calculate the number exactly right. All I care about is your swoosh in the right section? Okay, I'll do that in white because keep our graph in the same color. All right, so that's the outside sections that act like the previous problem. What happens in the middle? The middle has 3 options. The middle can be a parabola up, it can be a parabola down. Actually, it's 4 options because it could be a cubic, but the cubic can run either way. These are your 4 shape options for the middle, and sometimes the points will tell you. And sometimes you have to plug in some extra points. So I've got a value at 1/6 and at 2. So the question is, what of these shapes can I draw through those 2 points? Well, I know that I can draw, it looks like I could draw a cubic through there, right? That makes sense to me. But I also could draw a parabola, right? It could bounce off that 2 point. So the question is, which one is which? And in order to do that, where these graphs diverge is right here. Right here, it's either going to go up or it's going to go down. So I want to plug in that point, which is 3, and figure out which one is this. All right, so I get 1 over 9 minus 3 minus 12. This is going to be a negative number. So that means that this graph is not the pink part, right? It's going to be a cubic, and it's going to go through and down. So again, I don't care about exactness, just that that shape is correct in the middle. So this is kind of the worst case scenario where you have to plug in a point in each of the different sections. A lot of times when that happens when your horizontal asymptote's at 0. Other times you can use that process of elimination. So let's do one more. Let's do a 6-section one, and just what I would suggest here as I'm writing this down is that you pause the video and you try this one on your own, okay? Okay. So pause this and try it, and then check your work as we go along. All right, here we go. X-intercept. I'm going to set the function equal to 0, and if you've noticed by now, what happens is the denominator always just clears out when you multiply by it, and what you're left with is just the numerator. That's the pattern. It's been happening all along, so x equals 2 and -3. Those are my x-intercepts. I've got 2 of them. Y-intercept. I'm going to plug in 0 for x. Okay, so I'm going to get a -6 over -5, which is a +1 and a fifth, okay? That's my y-intercept. Vertical asymptotes. I set the denominator equal to 0. And look at that. It's already factored for me, so that's cool. X equals 5 and -1, so there's 2 of them again. It's going to be a 6-section problem. And horizontal asymptotes. Now, the horizontal asymptote process cannot be factored. Like you can do it that way, but it gets a little tricky algebraically. So what I would like you to do, and which will make your life easier, is take your function, if it is already factored, and multiply it out before you do your limit. So this is going to be x squared plus 3x minus 2x and a minus 6. And down here it's going to be x squared plus x minus 5x is a minus 4x and a minus 5. Okay, so that's my function, and now I'm going to take the limit as x goes to infinity of this guy. And I'm going to divide every term by x squared because that's the highest power in the denominator. And I'm going to do this one in my head and reduce as I go. So x squared divided by x squared is 1. X divided by x squared is 1 over x. 6 divided by x squared is 6 over x squared. X squared divided by x squared is 1. Negative 4x divided by x squared is negative 4 over x. And negative 5 over x squared is itself. As x gets very big, the 1 stays. These two things go to 0. The 1 down here stays, and these two things go to 0. So I get a horizontal asymptote of 1. All right, let's draw these and figure out if we need some extra points or not. My x-intercepts are 2 and -3. My y-intercept is 1 1/5. My vertical asymptote is going to be 5. My, and -1. I've got 2. There we go. And then my horizontal asymptote is going to be 1. Okay, so let's do our outside sections first. Let's start over here. Upper left or lower left? Well, there's a point right here. So that means that I must be in the lower left, doing that. And then right-hand side, upper right, lower right. Well, we can use process of elimination here because if I draw it in the lower right, I will have to cross this x-axis because eventually it has to grow up to the dotted line. So it will eventually have to pass that x-axis, and I don't have an x-intercept here. So I know that I can't draw it there. It has to be up here. Now, if that's hard for you to think that way, plug in a point. Plug in 3, 4, 5, 6 or 7, and you will get a positive value, and you'll know that it's the top section. Okay, what's happening in the middle? Well, it looks kind of similar to the last section. It looks like I might have a cubic here. I could have that, which is most likely, but I also could have a parabola that's bouncing off of there. And again, where these two graphs diverge is right here. You're either going to go up or you're going to go down. So 1, 2, 3, if I plug in x equals 4, then I should be able to tell what's happening. And again, all I need to do is know if it's positive or negative. So some of you guys might be able to just look at that and tell me. This is going to be 16 plus 4 minus 6. This is a positive value. And down here, I get 16 minus 5. This is a negative value. So I get a negative value overall. So that means that I'm down here, which means I am the white graph on this guy. And that's your picture right there. Okay, I'd like you to use graph paper on your homework. So try some of these. These are not easy at first, so be patient with yourself. Check your answers as you go, and we'll do some practice in class.